Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, TIFR, Jest, IIT-Jam and other exams related to physical science. Okay, so this is the lecture number 15th of electronics, okay, in which I'm going to discuss some questions of Zener diode, because Zener diode I have already explained in my previous lecture, and then I'm going to start transistor. Okay guys, so and also guys, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures which are going to help you to crack the exams related to physical science. And also guys, please share my lecture details with your friends so that they will also be able to watch my free live lectures and will be benefited from it. Okay, so let's get started. Meanwhile, just let me check whether I'm audible or not, then I'll proceed further so that they will also be able. Absolutely. Okay, so I'm audible, so I'm going to proceed further. Okay guys, so there are some questions remaining which I'm going to solve. So question 1 question is, that is Zener diode question. Okay, question is, I'll make a figure first. Okay, so this is the circuit. 16 volt is the potential here. Okay, and this is resistance is 1 kilo ohm. Okay, and output resistance is RL is 3 kilo ohm. 3 kilo ohm. Okay, and this Zener diode, this Zener voltage is this is Zener voltage is 10 volt. Okay, 10 volt. So now we need to find out V naught, guys. Okay, so V naught we need to find out. Okay, okay guys, so so simple guys, we need to find V naught, means we will remove the diode. Okay, for getting V naught. Okay, so means then it is going to be open circuited. Okay, I have already explained this in my previous lecture. So this is going to be, this circuit is going to be like this now. This part is open circuited. For getting output voltage, we will remove the diode from the circuit, Zener diode from the circuit. Okay, and that part will be open circuited then. Okay, this is 3 kilo ohm. This is 1 kilo ohm. This is 16 volt. Okay, this is the one. Okay, so removing diode, removing the because I have already explained it in earlier. Okay, so for V naught, we have removed the diode, and this became, now I'm writing directly. Okay, for V naught. So now in this circuit we'll use KVL. So by KVL, this is going to be 16 minus 1 into I. Let current is I. Okay, I This is IS, guys. This is IZ, and this is IL. Okay, we know. So this is going to be this one, 1 into I, and then this one, 3I minus 3I is going to be 0. So this is going to be 4I equal to 16, and from here the value of I is going to be 16 upon 4, that is 4 volt. Okay, so this is the voltage. Sorry, this is the current. My apology, it's 4 ampere, milliampere, because our resistance is in kilo ohm, right? So now I will find the voltage. So voltage, we know that output voltage is IL into RL. RL is given this 3 kilo ohm, and because this is open circuited, right? So this I is going to be IL, right? So I we have found it, that is 4 milliampere. So this value is going to be 4 into 3, right? 4 into 3, so this value is going to be 12 volt. Okay, 12 volt. And now since V naught, we can see the V naught is greater than VZ, that Zener voltage, right? VZ, it means diode is on. So that implies diode is on. Okay, that's what we check, right? Diode is on means diode is on means because it is telling the diode is on means this is 12 volt, right? So it means the V naught is going to be 10 volt, because V naught should be equal to that Zener volt, right? So V naught is 10 volt for this. Okay, this is the answer. Okay, so first we'll check V naught, and if it is greater than VZ, that is Zener voltage, it means diode is on, and then the answer for this V naught is going to be equal to that VZ, right? That is 10 volt means V naught is 10 volt. Okay, very good question. Okay, next question I'm going to solve. Before that, I'm going to explain something here. Okay, so this one. So if we have this Zener diode, okay, Zener diode, this is the Zener diode, okay, VZ, and this is equivalent to this one. If we write in terms of voltage, so this is going to be this one. This is plus part, this is minus part, this is the volt. Okay, this is VZ, right? This we can write. Okay, so this part is going to be plus part, and this part is going to be negative part for volt. Okay, so VZ. And similarly, this is important one, guys. Okay, similarly, so that we can easily solve question after knowing this. Okay, if we have Zener diode like this, okay, like this, Zener diode like this, in that case this VZ is going to be equivalent of this. Okay, this one, this is VZ. Okay, this is minus and this is plus. Okay, so this is VZ. So this part is going to be positive, and this part is going to be negative. If we make a this voltage, right? So this and this is VZ, this is VZ. Okay, in the Zener diode, and that is going to be equivalent of these two circuits. Okay, this is very important one. You need to know. So this part means positive for Zener voltage and this part is negative for Zener voltage. Okay. Now I'm going to solve one important question. Okay. So question is this one. So this is 16 volt. Okay, this is 1 kilo ohm. This is 3 kilo ohm. This is VZ. This is 10 volt. Okay, this one, and we need to find out P naught. Sorry, we need to find out this one. PZ we need to find. Okay, PZ. That is the power of Zener voltage. Okay, PZ. So this is the question, guys. Okay. Okay. So so I'm going to solve it. We need to find PZ. Okay. So we know PZ, that is that power of Zener voltage is going to be IZ into VZ, right? VZ is 10. So we know this is IS, this current, and this current is IZ, and this current is IF, load current, right? So here this is important one, guys. So Zener voltage at Zener voltage VZ is 10 volt here, right? It means the output voltage, this one, these are parallel, right? So this output voltage is going also going to be, this is 10 volt. Okay, this is important one. So we can write, since VZ is 10 volt, implies output voltage, that is V naught, is also 10 volt. Okay, this one, because they are in parallel, right? This is what we know. So now we will find this IS first. Okay, IS, current IS means, so this is I told you, right? This is Zener voltage, right? So this here the voltage is 10, 10 and 0. I told you here, right? If this is like this one, because if diode is like in this, if diode orientation is like this, in that case, this part is going for Zener voltage. This part is going to be positive, and this part is going to be negative. Okay, so it means this is positive, negative, right? So here the voltage is going to be 10 volt at this point. 10 volt, here is 0. 10 volt, and here we have 16 volt. Means at this point voltage is 16 volt. Now we need to find the current. Current I is going to be that voltage difference upon R, right? This we know. So IS, it means this is IS, right? So current IS is going to be voltage difference, means 16 minus 10 upon 1 kilo ohm, that is 1 kilo ohm, right? And so this value is going to be 6 upon 1 kilo ohm, right? And 6 upon 1 kilo ohm means this is 6 milliampere, 6 milliampere. Okay, so we have got IS, means this current, current in this part, right? Now we have got IS. Now we'll find this one, IL. Okay, IL is going to be very simple. IL current is going to be here. IL means this is this IL current flowing through this, means voltage difference, that output voltage we have, this is 10 volt, right? This is 10 volt here, 10 volt, this is 10 volt. Okay, 10 volt means that V upon I, right? V upon R, I equal to, so I is going to be V. V is 10 volt upon R is 3 ohm. R is 3 ohm, right? So this is going to be 10 by 3 milliampere. Okay. Now we know here Is, this current, right? This current is equal to this plus this, right? IL, right? So now we know Is is equal to Iz plus IL, right? Now we have Is, we have got it, right? Is, this is the Is, 6 milliampere. 6 is going to be Iz, we need to find out, and IL we have already found, this is 10 by 3, right? So from here Iz is going to be 6 minus 10 by 3, 6 minus 10 by 3, so this value is going to be 8 by 3 milliampere, right? 8 by 3 milliampere. So now we can easily find out Pz. Pz is going to be Iz into Vz, right? Vz we have already, we have the value, there is 10 volt. So Iz, this is going to be 8 by 3 into 10, that is going to be 80 by 3 milliwatt, right? This is 80 by 3 milliwatt. This is the answer, guys. I hope, guys, you have understood it. Okay, this is the one. Next is, okay, so Zener diode is completed, guys. Now I'm starting transistor. Okay, transistor. 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 Okay. Transistor. Okay. So I'll make a diagram for transistor. Okay. Suppose I'll make this one PNP transistor. Okay. This is PNP transistor. Okay. PN. I can write like this. This is PNP transistor, and there are it's P part, right? So there are holes, and there are electrons. Okay, and there are holes. So this is NPN transistor. Okay, this part is called this part is collector, this part is emitter, and this part is base. Okay, so in PNP transistor, the current flows, majority of current flows because of majority of charges, right? And these are majority of holes. Okay, so because of so there's a current because of majority of holes. Okay, so because of holes, the current starts flowing. Okay, so this is NPN transistor, guys. Very simple thing. We have already studied it in class 11, 12, right? In BSc, MSc. So this is NPN transistor. So there are holes, and in P part there are holes, there are electrons. Okay, and if they would be biasing, then current will flow, and because of majority of holes. Okay. Okay. Next, I'll make this one. So NPN transistor symbol I will make. So this is the one of the transistor I'm going to make. So this is base, guys, and this is collector, okay, and this is emitter, okay, and this is emitter, okay, and this is this one PNP, right? So this is N, this is NPN I'm talking about, N, and this is N, and this is P, okay, base is P, okay, this one. So in this case, current direction will be like this, P to N, okay. This is NPN transistor, and if you talk about PNP transistor, then the symbol is going to be like this. Simple things, basic things. Okay, so this is base, this is collector, this is emitter. Okay, and direction, and this is P part, this is P, this is PNP transistor and transistor. Okay, and this is N, this is P N, right? And the direction of current will be P to N, right? So this one, this is direction. So this is emitter, this is base, this is, so this is NPN transistor symbol, okay, and NPN transistor, and this is PNP transistor. This is PNP transistor. This is PNP transistor, and this is NPN transistor. Okay, this one. Okay, next. Okay, guys. So here I'll do the biasing as well. So we have this PNP transistor. This one. These are holes. And these are electrons. Electrons will be there as well. Okay, and this is the holes will go like this. Okay, and this is the biasing, positive, negative, and this is B. This is going to be negative, positive, minus, plus. Okay, so this is P, PNP, PN, PNP transistor, and there the current flows because of majority of holes. Okay, flow of holes. Okay, and this is emitter, this is base, and this is collector. Okay, so here BE, this is BE. BE is forward bias plus, right? B is forward biased, and BC, This is BC. BC is this positive, this negative, right? So this is reverse bias. Okay, so this is the biasing of PNP transistor, right? This is a flow, and this part, this EB part will be forward bias, and BC part will be reverse bias. Okay, so this is the biasing. Next, in this case, this is IC, IE, that emitter current is going to be equal to IB plus IC. Okay, so emitter current is equal to this one, base current plus collector current. Very important formula, guys, you need to note down. Okay, we'll solve question using this formula. So I equal to IB plus IC. I equal to IB plus IC. Next, here IB current is due to recombination. Okay, due to recombination. Due to recombination of holes and this electrons, right? Okay, so this is IB equal to due to recombination. Due to recombination, and this is very less. IB current is very less, guys. Okay, so IB is due to recombination. This one, IB current. Okay, next is and because this is very less, IB is very less, so we can say emitter current is almost equal to IC, that is collector current. Okay, this is also important because IB is very less. And also, guys, IC current, IC is going to be IC because of majority of charges. Okay, majority charge carrier, because of majority charge carrier, plus IC because of minority charge carrier. Okay, minority charge carrier, or I just write minority. Okay, minority charge carriers. And here this one is because of this is IC, which is because of minority charges. It is temperature sensitive, guys. Okay, temperature sensitive. It depends on temperature, right? So it's a temperature sensitive. So IC is IC because of majority charge carriers, and this IC because of minority charge carriers. Okay, so here it's PNP transistor, so the majority charge carriers are holes. Okay, and minority charge carriers are electrons. Okay, so here majority charge carriers are holes. So these are important results, guys. Next, we can write the IC is, because this is very less, guys. IC is almost equal. This is very less, so IC is almost equal to IC because of majority charge carrier. Majority charge carrier. Okay. This is IC almost equal to IC. This IC that majority of charge because of majority charge carrier. Okay, so that is almost equal to this because of majority charge carriers. Okay, now is common base configuration. I'm going to explain. Common base common base configuration. Common base configuration. Okay. So common base configuration. So I'll make a figure first. So this is a PNP transistor. Okay. PNP transistor. This is N. This is P, and this is P. Okay. And common base means base will be common, right? Okay. So this is the one. This one, and this is the one. Okay. So this is P and P. Okay. So this is emitter. This is base, and this is collector. Okay. And here B is the this PNP transistor, and you can see this is BEB, BEB, VEB. My apologies, VEB voltage I'm talking about. VEB, VEB, and this is VCB, VCB. Okay, because base is this common base is common. Okay, common base configuration for PNP. Okay, this one. This is forward bias, this is reverse bias. Okay, and similarly we'll make this NPN transistor. Okay, configuration and biasing for common base configuration. Okay, this one. Okay, base is common. Okay, so this is N, this is N, and this is NPN. Okay, so here the direction will be P to N, right? This is direction. So this is emitter, this is collector. Okay, and this is base. Okay, okay, and then this is the voltage, and this is also okay. So this voltage is this voltage is this one, V BE, VBE for NPN, VBE, and this is VCB or VBC, VBC, VBC. Okay, okay, so this is the one. This is NPN transistor bias. Okay, for common base. The common base NPN transistor. Okay, common base NPN configuration. Okay, well, this is the one. Okay, so now the important thing I'm going to discuss, and that is input characteristic, guys. Okay, for common base configuration. Okay, input characteristics. Input characteristics. Input characteristics. Okay, input characteristics. this is IE, and this is VEB, VEB. This is IB, this is VEB for PNP, okay? VEB, okay, and the input characteristic graph I'm going to draw, and this is going to be between IE at emitter current versus this voltage VEB, okay, and this graph is going to be like this. This is the input characteristic curve, okay, and this is the input characteristics versus this curve is the IE versus VEB, okay, emitter current versus that VEB voltage, okay, and here guys we need to understand VCB. VCB is 0. Here VCB is uh, VCB equal to 0. VCB equal to minus 5 volt, and this is VCB equal to minus 10 volt, okay. So this is the input characteristics, okay, for common base configuration for a PNP transistor, okay. And here guys you need to understand one thing, that this is the graph between I versus EB, and keeping VCB constant, okay. So this is the input characteristics, okay. Input characteristic means the graph between IE versus EB, okay, keeping VCB constant, okay. So this is the input characteristic graph guys, very important, you need to note down guys, okay. And the slope is going to be here, slope is going to be delta IE upon delta VEB, delta IE upon delta VEB, delta IE upon delta VEB, okay, VEB. So this is the slope guys, and this is the input characteristic graph, very important, okay. Okay, next is output characteristic graph, okay. This is very important, output characteristics, okay. So output characteristics, so this is important graph. This graph is going to be IC versus VCB, okay, IC versus VCB, okay, and this graph is going to be this one. So here we'll take -2 negative side, okay, minus 2, -4, -6, -8, -10, -12, okay, and this is going to be -2, and this is -4. So just +2, and +4, okay, this one. So if we draw the graph is going to be like this. This is the graph, guys. This is the output characteristics. This is output characteristics. Okay, output characteristics, IC versus VCB. Okay, and this graph is very important, guys. So this region is called cutoff region. Cutoff region. In cutoff region, this both are reverse bias. This one, okay, in cutoff region, and both will be reverse bias. Okay, reverse bias. This is the cutoff region. Next, this is active region. Okay, this is active region. Active region, and this is amplifier. Okay, because it amplifies voltage and power. This is amplifier. Okay, guys, just give me 1 minute. There's some issue. Okay, guys, so this one, so this is the cutoff region. Okay, this is cutoff region, and this is active region, and this is the amplifier, because this part is amplifies, right? Amplifies voltage and power. So amplifier, this is amplifier, and this region is the saturated region, right? Okay, saturated region. Okay, so this is saturated region, and in this case, in saturated region, both are FB. Okay, forward bias. Both means this VEB and VCB. Okay, VEB and VCB. Okay, this one, VEB and VCB. And so this is in active region. In active region, VEB is reverse, that forward bias. Okay, so this is forward bias. This is forward bias, and VEB is VCB. VCB is reverse bias. VCB is reverse biased. Okay, VCB is reverse biased. Okay, so this is cutoff region, guys, very important. In this case, both are reverse bias, means VCB and VEB both are reverse bias, and this is saturation region, guys, and in this case, both EB and VCB both are forward bias. In active region, which amplifies things, right? In this case, VEB is forward bias, and VCB is reverse bias. Okay, this is important curve. Okay, and many questions are asked in the examinations. Okay, now I will discuss, and also guys, this is important one. Here IE will be constant. Okay, so this is graph between IC versus VCB, and IE, this emitter current IE is constant, and this is 2 milliampere here, and this is I equal to 2 milliampere. This is 2 milliampere, and this is 0 milliampere. Okay, this is 0. I equal to 0, and here IE is going to be, this is 10 milliampere. Okay, IE is 10 milliampere. IE is 10 milliampere. Okay, and IE is 2 milliampere, and IE is 0 milliampere. Okay, so this is the output characteristics for common base configuration is this, and this is the graph between IC versus VCB. Okay, okay guys, so next we'll find this alpha, that is current gain. Okay, alpha, current gain, that is alpha. Okay, alpha value is going to be IC upon IE. Okay, emitter current, collector current versus emitter current at this VCB is constant. Okay, VCB is constant. Okay, VCB is constant. So VCB is constant. So this value, obviously I is greater than IC, right? Because I equal to IB plus IC. So this means current gain for current gain, that is current gain for common bias, I'll write in CB, for common bias configuration. Okay, alpha, that is less than equal to 1, because I is greater than, since IE is greater than IC. Okay, so less than 1. Okay, and output resistance, if we talk about output resistance, output resistance output resistance output resistance, that is R naught, is going to be this is R naught is going to be, that is delta VCB upon delta IC. This is the output resistance. Okay, well, delta VCB upon delta IC, and this is going to be 1 upon slope. Okay, slope, because slope is delta IC upon delta VCB, and that is very less. Okay, slope is very less. So slope is very less. It means this value is going to be very high, very less. So it means this one R naught, that is R output I'm talking about. Okay, output resistance R naught equal to very high. R naught is very high. Okay, R naught is very high, and that is in mega ohm range. Okay, mega ohm range. And similarly R in, that is input resistance, that is going to be delta VEB upon delta IE, and this is 1 upon slope, because slope is delta IE upon delta VCB. Okay, and this is high, guys. Slope is high. Okay, so this means, this implies R in is low. This is very important result. Okay, this is high, and this is low. Rin is input resistance is low and output resistance is high. Okay, and now we can find this V output, and that V output is going to be IC into R output, right? V output IC into R output, and that value is going to be, okay, this is V output, guys. Okay, V output, and similarly V input is going to be V in. V in is going to be IC into R input, IC into R input, right? IC into R input. This is and IC is very less, right? So this means these are very important results. Okay, you need to note down. So V output is IC into R naught and V input is IC into R in. This is the common base configuration we are studying. Okay, and now so since we know this one IE IC, that is IC is almost equal to IE, right? Almost equal to IC is almost equal to IE. So it means, I'll write in next page, it means okay, this also you need to understand this here. R in low and R output is high, right? So this means V output is greater than V in. Similarly here R in low and R in low, right? And so that means this one here I can write here also, next one. So that is okay, guys. So here I can write, since R output is greater than R input, implies V output is greater than V input. Okay, and similarly this this one P output is greater than P input, because V output is greater than R output is greater than, right? So we know P output is V output and R output, right? So this means P output is greater than P input. Okay, and V output is greater than V input. So this means what it says? It says this common base configuration works as a voltage amplifier, or power amplifier. Okay, voltage amplifier or power amplifier. Okay, so it works as a voltage amplifier or power amplifier. Okay, guys, so I hope you have understood it. Next is common emitter configuration. Okay, common emitter configuration. Okay, so common emitter configuration. So we have studied a common base configuration. Now we are going to study common base configuration. Okay, so I'll make a figure. So this is transistor. Okay, so guys, this is base and this is collector. Okay, and this is emitter. Okay, this is emitter. This is emitter. So this one. Okay, so this is emitter and this is current direction. So this is NPN transistor, guys. This is N, this is N, and this is P. Okay, NPN transistor, and this is emitter E, and this is collector C. Okay, this is collector C. And this is NPN transistor. So this is VBE, and this is VCE. VCE. Okay, VCE. Okay, guys. So this is the common emitter configuration. So this emitter is common, guys. Okay, this is the direction, and this is P to N. This is the direction. Okay, so this is a common emitter configuration. This is E, and this is VCE. This is VBE. Okay, this is collector. This is emitter, and this is base. Okay, so now I will discuss this one, input characteristics for common emitter configuration. Okay, input characteristics. Input characteristics. Input characteristics. Okay, so input characteristics means we'll draw the graph. We'll draw the graph between this VBE versus IB. Okay, because the emitter is common, VBE versus IB. Okay, and so this graph is going to be keeping VCB constant. Okay, so this graph is going to be this one, similar to common base configuration. Okay, this is the input configuration. So these are not looking straight lines. Okay, so these are like this. Okay, so this is the graph, and here VCB or VBC, VCE, okay, and VCE and VCE. This is constant, guys. Okay, so since VCE is constant, VCE constant. Okay. Okay, so this is the graph, or we can write this one as well. This is 0.5 volt. Okay, so this is the input characteristics for common emitter configuration. Okay, so here the graph is between IB versus VBE. IB versus VBE, and okay, keeping VCE common, okay, VCE constant, VCE constant. Okay, so this is input characteristics for common emitter configuration. Now output characteristics, output characteristics. So output characteristics I'm going to draw, okay. Output characteristics, it's important one. Okay, so this is the output characteristics for common emitter is IC versus VCE, right, VCE. IC versus VCE, right, and this was IC versus IB versus VB. Okay, so now this is IC versus VCE. Okay, so here I'll make a diagram. So this is going to be like this. Okay, so this is the graph. This is the graph, guys. Okay, so here this one, this point is going to be like this. Okay, so and this line is going to be like this here. This is the line, okay, and so this region is going to be saturated region, saturated region, saturated region. Okay, this is the saturated region, guys, and this is active region, active region. Okay, here this one VBE is forward bias, and VCE is reverse bias in active region. Okay, so this is cutoff region, and both reverse bias, both means VBE and VCE, and here both forward bias inside in this is the saturation region, guys. This is saturation region, right, saturation region. Okay, this is saturation region and both forward biased. Okay, this is cutoff region, both reverse bias, and this is active region. Okay, here you need to understand this is the graph between IC versus VCE. Okay, and this is for common emitter, and also, guys, here IB. Okay, IB base current is constant, and this value is IB is 0 here. IB value is 50 micro ohm, and IB value is 100 microampere. My apologies, it's 100 microampere, 50 microampere, and this is 0. Okay, so this is the output characteristics. Okay, output characteristics of common emitter configuration, and this part is saturated region, guys. Okay, okay, so this is the one. Now we'll find this one, this current gain. Okay, so current gain beta, this value is going to be this one. We know, right? IC upon IE. My apologies, IC upon IB, because I is common emitter, means IB, IC upon IB, IC upon IB, right? And which is, by IB is very less, right? Which is greater than 1, right? So it means this implies this is current amplifier. Okay, it amplifies the current amplifier, and also this is current amplifier, and this is also voltage amplifier. Okay, so if you get R in is going to be delta VBE upon delta this one, delta IB, and that is low value. Okay, low value. And R naught means R in means input resistance or input impedance. Okay, our output is going to be delta VCE upon delta IC, right? And this is high resistance, output resistance is high and impedance resistance is low, so it means this is voltage amplifier as well. Okay, so in the both cases, common configuration and common emitter configuration and common base configuration, we have seen the R output, the output resistance is high and input resistance is low. Okay, so well guys, before wrapping up the class, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures, which are going to help you to crack the exams related to physical science. Okay, and also guys, I would request these students, please share my lecture details with your friends so that they will also be able to watch my free live lectures and will be benefited from it. Okay guys, thank you so much. Bye now.